Okay, so having a look through the more questions on phenols this time. So this was just bringing some more ideas and particularly having a look at the tests as well that you learned during the lesson. So question 1, for each of the following compounds, give a test which will give a positive result for that compound only. So that's a critical bit here. So first one, we're testing for phenol. So test for phenol is to shake with bromine water. And you need 2 observations here. We need it to turn from orange to colourless for 1 observation, and that we get a white precipitate for the 2nd observation. With B, so having a look along here, so we've got our secondary alcohol group here. So we can oxidize that. We can't oxidize anything else here. So we're going to warm with acidified potassium dichromate, and that will turn from orange to green. So make sure you give these changes, what it was before and what it turns to. And then we have got our carboxylic acid group here. So we are going to add sodium carbonate and we will see effervescence. So remember that we choose sodium carbonate here, not putting sodium in, because had it been a phenol, we don't want to see any effervescence. So we need to choose something that will only give this positive result with this functional group. So the effervescence here. So then on our explanations, so we need to explain why phenol is much more acidic than ethanol. And when we were learning about this, and I'm just going to draw on the whiteboard so I don't destroy my mark scheme here, we excuse me, we had a look about how the negative charge on the ions can be delocalized, giving greater stability. So if we take, for example, ethanol, and we remove the H, as in if it was behaving as an acid, we would get C2H5O minus and H plus. So the negative charge here is firmly on the oxygen. There's no delocalization possible. So with our phenoxide, with our phenol, I'm then producing the phenoxide ion. So our O minus there and our H plus. Then we had a look at how the lone pair of electrons can be delocalized into the ring, but we did have a look at some diagrams which are showing how that pair of electrons can effectively come in having a double bond here. And then if we remember and go for the Kekulé structure like this, then we can kind of keep shifting the double bond around. And this is showing how our electrons are effectively becoming free to move around the whole structure, because then while we've put them here, they can keep moving around further and so on. So the delocalization of the lone pair of electrons in the p orbital on the oxygen into the ring gives us a much more stable phenoxide ion. The stability of this means that the equilibrium position lies further to the right-hand side, and so we have more H plus ions, so it's going to be more acidic. So in terms of words on paper, so we could say that the negative charge of the phenoxide ion can be delocalized into the benzene ring. The phenoxide ion is stabilized, and so the equilibrium position lies further to the right than it would do with ethanol, where there's no stabilization of the ethoxide ion. So why phenol reacts with bromine water without a catalyst, but methylbenzene does not. So this is essentially now looking at why phenol is more reactive than benzene. So like on the previous question sheet, we need to explain that the lone pair of electrons on the p orbital of oxygen, not on the OH of oxygen, is delocalized into the ring. We need to explain that that increases the electron density. And then we could say that our bromine will be polarized enough so that it reacts directly, or it will be attracted strongly enough to react directly. And then why phenol is not oxidized by acidified potassium dichromate, but then we said up here that the OH on the carbon chain was, that is because if we are going to introduce a C double bond O here, we're going to have to break the ring because we haven't got enough bonds to be able to do that. So oxidation by the acidified potassium dichromate would require the ring to break, and it's stable, so that's not going to be possible. So throwing in a little bit of spectroscopy next. So draw the displayed formula of 2-methylphenol and the display formula of methoxybenzene, which are both isomers of C7H8O. So 2-methylphenol we've got here, and the methoxybenzene. So we've got an ethoxy group here, so the O, and then the methyl group, so methoxy there. Then when we're explaining how spectroscopy can be used, we need to make sure we specify which one we're talking about and the differences. So we're wanting to look at how we can distinguish between these two compounds. So it's no good just listing lots of peaks you will have. We want to know how we're going to spot the difference. So to spot the difference, we've got an OH group, which we're used to being a significant peak. So the broad peak between 3,200 and 3,550 there, can't read my numbers, and it's not present in here. So we need to say that we'll get a peak due to the OH in this region, and it will be present from structure 1 only, or it would be absent in the other one. So we need to make it very clear what we're talking about there. Then, if we're trying to distinguish between these two in mass spectroscopy, again, we need to look at what we're going to get. And as I was working through here, then you see that some of the peaks are going to be the same. So we need to look for where we've got differences. So from both structures, we get obviously the same molecular ion peak. And then if you take off the CH3 groups, then you get the same peak too. The actual structures are different, but the peaks will be the same because they've got the same mass. So we can then look further and see what's possible. So going back to this one, instead of removing a methyl group, we could remove the OH group. So it means we've taken off 17. So take 17 away from 108 and we get a peak at 91. And we say what the fragment's due to, and we make sure we have a positive charge. And then this side, we can take off the whole CH3O, and once we do that, we're left with C6H5+, which will be a mass of 77. So in terms of distinguishing these, we can say that isomer 1 will have a peak at 91 due to this group, which the other one won't, and isomer 2 will have a peak at 77 due to this group, which this one can't have. Okay, so it's just being really specific so that we can tell the differences here. Then we had a little bit of synthesis in our question here. So we need to work out what we're going to form when we react these things together. So if we take phenol and react it with chlorine water, we can get the tri-substitution product here. So remember, the phenol is much more reactive than benzene. So we don't need the halogen carrier, so chlorine water is fine, and we can have our tri-substitution giving us our product there. And then when we have sodium hydroxide coming in here, if this was a normal haloalkane, we could have a nucleophilic substitution of the Cls, but we have the additional stability here, so we don't have nucleophilic substitution reactions going on. So the chlorines are left alone here. But what we do have is the acidic H in the phenol group. So we've got an acid-base reaction going on, and we produce our sodium phenoxide here. Okay, now the mark scheme is available to you on SharePoint and on Teams. So obviously you can just whip back through the video if you want to use it on your screen here. If you have any questions about any of this, we haven't done it as a live return this time because this is starting to clash with both Year 10 and your lessons in school. So we want to make sure it's easily accessed for everybody. But if you have any questions at all, then email a teacher directly or post on the Year 12 team with a question and we'll reply to it as quickly as we can. I'm sure any questions posted on the Year 12 team will be appreciated by other people who will probably read them and find them useful as well. So do get in touch if you've got anything on this and on the first questions on phenols as well. Anything you want to clarify, do get in touch.